Welcome guys, we're going to be going through this stats paper for 2023 and then after this I'm going to upload the mechanics one, so watch that one right after. Let's get started. Pause the video, have a read of the question. If you've already kind of looked at the paper, great, but this is a Venn diagram question where P and Q are probabilities, shows that 3 events blah blah blah. We want to find the probability of A. First question is pretty simple. It's nothing too complicated. It's just looking at, well, what is the probabilities of these two numbers added together, 0.13 and 0.25, because that's within the probability of A here, so that's going to be 0.38 in total. Next question, the events B and C are independent. I'm going to stop right there, and I'm actually going to write down my independent formula. And I think it's a good habit to kind of write down the formulas when you can. When you have two events multiplied together and they're independent, they make the intersection of those two events. You might be used to these being A and B, but I'm just writing it in the context of this question. It's exactly the same thing. Well, probability of B is all of this circle here. And that's going to be, this is 0.25 plus 0.05 makes 0.3. And I add this together, this makes 0.6. And you can add that in your calculator, and that should give you 0.6 for probability of B. Probability of C is this circle here, so that's going to be 0.3 plus P. I'm going to put this in brackets. Be careful about that because that's the whole probability of C, and that equals to B and C, and where B and C is this middle section here, which is 0.3. So I'm just going to put in 0.3 here. Now there's two ways you can do this. You can expand the brackets and rearrange for P. Or what I'm going to do is write it like this. It's because we are multiplying here, right? So why can't we go ahead and just divide? So why can't we do 0.3 divided by 0.6, which gives us a half, I believe. A half, 0.5. So because we are timesing here, we can just do divide, and that can get rid of the coefficient on the outside of the brackets. And that gives us 0.5. Therefore, P is equal to 0.2. Cool. Now, whenever you have probabilities questions, I think it's a good habit to also write on the side that all your probabilities equal to 1. And I think sometimes it's just overlooked, even though it's such a simple thing. And that just means that when you add all these probabilities together, they add up to 1. Well, we worked out P, we also need to work out the value of Q as well. So, I'm going to add all the probabilities together. So this gives us 0.13 plus 0.25 plus 0.05 plus 0.3. We worked out what P was just now, which is 0.2. Oops, forgot to add. This gives me 0.93. How much is left over for to make 1? 0.07. So that means that Q must equal to 0.07. Cool. I should probably write all the numbers down in terms of working out. So I'm just going to put 0.25 blah 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 is equal to 0.93, and therefore Q is equal to 0.07. Okay, that's part B also complete. Part C. Now I would recommend that you use a formula for part C. You can do it without, but with a formula I think it just stays consistent and accurate. So the formula for probability of A given B is kind of given to you in the formula, but I don't really like the way it's given. It's a really complicated version. So I would recommend that you just remember this: probability of A and B divided by probability of B for A given B. Okay, so in this case, the question is asking for A given B prime. So the probability that A given not B is the same thing as probability of A and not B divided by probability of not B. Cool. Now we need to find out essentially what is this? What is this? I think a good place to start is thinking about what or where is B prime or not B. I'll just be using the terms interchangeably. They're the same thing. Where is not B? Well, B is this circle here. So everything on the outside, which is this, which is this, and which is this, that is not B. Okay, cool. Now, to be fair, we do actually need to use this for the formula, so I'm just going to substitute it into this denominator. And then we'll use that for the numerator in a second. But for the denominator, that's going to be 0.13 plus P plus Q. That's going to be, I'm just going to write this 0.13 plus Q plus P. We already worked out Q was 0.07, and P is 0.2. That gives us 0.4, because this is 0.2. 0.2 plus 0.2 gives you 0.4. So we're going to have 0.4 on the denominator. Okay, perfect. Now on the numerator, if we go back to the idea of not B, we need to figure out, well, where is A and not B. Now within this section of not B, we are trying to find out the overlap of where is it A at the same time. But within the section, the only place where it's A at the same time is this section here. And the only probability within this section is 0.13. So we're just going to put 0.13 on the numerator. And if you simplify this, you can kind of just do a bit of, you can see what this probably would be. This would be 13 over 40. Does it simplify? 13 is a prime, so I'm going to say no, but you can leave it like this. Okay, and that's going to be a final answer for part C. Okay, for question 2, it says a machine fills packets with sweets, and 1/7 of it, of the packets also contain a price. The packets of the sweets are placed in boxes before being delivered to shops. There are 40 packets of sweets within each box. So just by looking at this statement here and this 1/7, this has already told me that, well, it's probably going to be to do with binomial distribution. Okay, and just by looking at, well, part A, it just say it can be binomial distribution. So to kind of think about, well, what sort of conditions we need, there are a couple, and you should always talk in terms of the context of the question. So the first thing that comes to mind is independency. Okay, and specifically in terms of the context of the question, what is being independent? Well, it's the prizes being in the packets that are independent. Okay, so you would say independent packing of prizes in the packets. But you can also say random. Random also works. Okay, and you should probably also talk about constant probability, because that is also a key bit. You don't want different probabilities for each packet. So it's a constant probability that a packet contains a price. Contains a price. That's it. Those are your two bits. You don't need both of them, obviously, it's just a one marker, but I think these two either just get you the mark. Okay, part B. A box is selected at random. For using using this binomial distribution, find the probability that the box has exactly 6 packets containing a price. Let me get the calculator up real quick. Okay, now I will be using the CG50 quite a bit, in fact, all the time. But I will show you kind of briefly how to do it on the normal or the calculators. So, because we're trying to find out that probability that t is equal to 6, in the other calculator you can use BPD, okay, and then just set it to 6. Our sample size is 40, and we're going to be doing 1/7, and we should just get the probability of 0.1727. Cool. Part II. So what you want is the probability that t is less than 3, which is equal to probability that t is less than equal to 2. Okay, what you're going to do is go to your calculator, and this time you're going to be using BCD. Now you can just type in 2 straight away, but since the binomial distribution in the CG50 gives you a bit more control, your lower is going to be 0 and your upper is going to be 2. Same sample size, same probability, equals, and you should end up with this probability 0.06158 or 0.06159 if you round that. Okay, and that should also get you full marks. Okay, part C. Camel's Sweet Shop buys 5 boxes of sweets
find the probability that exactly two of these 5 boxes have fewer than 3 packets containing a prize. Okay, so when you do stats questions, try to spot like a key phrase that is in common between different questions. And you can see this phrase here, fewer than 3 packets. We've already looked at this before. Okay, so we actually have a probability that we already worked out for this, which is 0.06159 for one packet, for 40 packets, for a packet containing a prize. Okay, so when you write a distribution down, I would recommend you actually just try to look at or even annotate what the event represents. So your T event here, what you have here is essentially the probability a packet contains a prize. That's what this represents. Okay, now this distribution here, if we make a new distribution, what we can do is, let's use x. X is binomially distributed with 5, and I'm going to choose this probability here, 0.06159. Okay, and the more decimal places, the better, it becomes more accurate. And this represents, okay, that a box contains fewer than 3 packets with a prize. Okay, the key difference between these two events is that X has a box, okay, whereas T is just talking about the packets themselves. Okay, so that's the difference, and you can just take this probability and insert it into here. Well, part C is just asking for exactly 2, so what you're going to do is probability that X is equal to 2. Okay, we're going to go into our calculator. Okay, use BPD, distribution, binomial BPD, 2, 5, 0.06159. Obviously, the more decimal places, the better. But using that probability, that gives you 0.0315. 0.31. 315? 3135, sorry. 3135. Cool. Okay. Next, we have some hypothesis testing for part D. So Camel claims that the proportion of packets containing a prize is less than 1/7. A random sample of 110 packets, this is our sample size, is taken, and 9 packets, so this is our key value, packets contain a prize. Use a suitable test to assess Camel's claim. So this is a hypothesis testing question, and our significance level is going to be 5%. And you can apply this method for every single, in fact, I'll say about 75%, just because there is, critical regions in some questions. In this question, you don't have to work out the critical region, but hopefully, if in this paper there is a normal distribution question, if you have a normal distribution question, you don't need it. Anyway, let's continue on. Okay, the first thing what we need to do is define our H0, which is going to be probability is equal to 1/7. Okay, we just pick the same probability that's kind of given to us in the question. Okay, and then we just use that across, and it needs to always be equal to. Okay, we're assuming the fact, okay, if our assumption is wrong, then the probability is just that probability. Our alternate assumption, which is the actual assumption we're making, is that the proportion less than 1/7. That means that our probability is going to be less than 1/7. Then what we're going to do is write down the distribution. Our sample size is 110, and our probability, we just take this probability into there. Okay, now what we can do is we can work out a probability using this key value here. So what I'm going to work out is the following. Probability that X is something of 9. Now we need to choose less than, bigger than, which one. We're always going to be doing the same symbol as this, unless it's a not equal to, but we'll get to that. Either if it's going to be a bigger than, we're going to do bigger than or equal to. If it's a less than, we're going to be doing a less than or equal to. So in this case, it's less than, and it always needs to be an equal to sign there. Okay, always. All right, and we work out this probability. Now let's go into our calculator. We're going to go to BCD, binomial CD, 0 and 9. In your other calculator, you can just put 9. Our sample size is 110, and our probability is 1/7. this is going to equal to 0.03829. Cool. And you can see that this is going to be less than your probability, or your significance level given to us in the question, which is 5%. Therefore, because it's less than 5%, it's significant. So we're going to say reject H naught significant, or you can just say, yeah, you could just say reject H naught, or you could say it's significant. They basically mean the same thing. And then you're going to say there is evidence to support what's Camel's claim. Camel's claim is the packets containing a prize is or the proportion of packets containing a prize is less than 1/7. Camel's claim of the proportion of packets containing a prize is less than 1/7. Okay, you can just kind of copy the script that they give you in the question, and that's going to give you full marks. Question 3 here. We've got a large data set question, and it's saying that we've got X millimeters, and we were looking at rainfall here, in Leeming. Now, Leeming is a place in the northwest of England. So I believe that is good to know in terms of your large data set. And whenever you have something called TR, essentially what TR represents is, well, it's an abbreviation of trace, so meaning trace of rain. And essentially it's a range of your rainfall between 0 and 0.05 millimeters. Now, if you ever get this in your exam, just convert the TR to 0. Okay, it's the easiest one to work with, and then we can combine the data and actually make it usable. At the moment, it's not usable because it's just in letters. Okay, part A. And actually, part A is just what we've just talked about now. Explain how the data will need to be cleaned before Ben can start to calculate statistics such as the mean and the standard deviation. It's just about the trace. The trace is at the moment, it's not a numerical value. A numerical value at the moment. Okay, so we can do TR is equal or set TR to 0 millimeters. Okay, cool. Part B, calculate estimates for the mean daily rainfall. So we need to work out the mean. So the mean, we know that the mean is going to be sum of x over n, and this is our notation for this. So our sum of x is already given to us, which is 390. Our n is going to be our total frequency. So it's going to be all of the frequencies added together. Let me just check if they've given it to us here. They haven't. So I'm just going to add them manually. So 55 plus 18 plus 18 plus 21 plus 17 plus 9 plus 9 plus 6 plus 2 plus 29. That gives me 184. And if I put that into my calculator, 390 divided by 184. And that gives me 2.12 millimeters of rain. Part II, that's our standard deviation. And our standard deviation is just a formula that's also in your formula book. That's going to be square root of, or the summation of, yes, square root of the summation of x squared f all over n minus your mean squared. This is in your formula book. Now they've given us this x squared, and in this case we don't actually need f, since it's not really a frequency table like that, I guess. But it is a frequency table, but you don't need to multiply it up. So we can just take this value that they've given us. So that's going to be the square root of 4336 over, well, we've already worked out the value of n, which was 184, minus 2.12 squared. And if I put this into my calculator, square root of 4336, 184, minus, I'm going to use my answer so it stays as accurate as possible, equals, and that gives me 4.367 millimeters. Try to keep your units there. Sometimes they just will mark you down for your units. Just try to add it. Part C, Ben suggests that using the statistics calculated in Part BI to estimate the annual mean daily rainfall in Leeming, give a reason why the data is not suitable. It's because we cannot work out the annual mean of the daily rainfall, because the way that the large data set works, essentially, we don't have every single month. Okay, the question's asking us about the annual mean. We can only do that if we have every single month. In the large data set, it's only between these months, specifically May to October. Okay, so between that, so it's part II, state giving a reason how you would expect the estimate to differ from the actual annual mean. And because in the UK you would expect that it rains a lot more in the winter months, like September, December, around that time. I mean, we don't really get snow, do we? But so around like December time, for example, December or winter months are not recorded in large data set. Recorded in large data set where rain is more expected. So your annual mean is probably going to be lower, so it's probably going to be some sort of underestimate. So annual mean, though the data we have currently in kind of your, not necessarily summer months, but these type of months, would be less than expected. I think I probably just put underestimate, would be an underestimate. I think that's probably a better word just to summarize that. There we go. Okay, perfect. Let's move on. Question 4. Just by looking at this, scanning this, this looks like a normal distribution question. A study was made of adult men from region A of a country. It was found that their heights were normally distributed with a mean of 175.4 and the standard deviation was 6.8. Okay, the first thing what I'm going to do is just write down the standard deviation, the normal distribution. That should be an n, and that's going to be 175.4, comma 6.8 squared. Find the proportion of these men that are taller than 180 centimeters. We're going to be doing probability that x is bigger than 180, and we can just put this into our calculator straight away. So into our calculator, we can do distribution, normal, NCD. And we're going to be doing 180. Now, for as the lower, as the upper, you want to put a really, really big value. Because the way that normal distribution works, because it's continuous, we can essentially have infinite values. So you need to put a really, really large number. Essentially, you put infinity, but obviously you can't put infinity, so you just put a bunch of 9s. And we get this probability 0.1617. Okay, that's going to be our... Ooh, I've actually put in the wrong areas. Your mu is your mean, and your standard deviation is your sigma here. So this should be 6.8. There we go, 0.249. Now for part B, we've got a hypothesis testing. It says that a student claimed that the mean height of adult men from region B of this country was different. So this is probably going to be a not equals to or two-tailed test from the mean height of adult men from region A. Okay, a random sample size of 52 adult men from region B had a mean height of 177.2. The student assumed that the standard deviation of the heights was 6.8 for both A and B, and we need to do a test, and our significance level is 5%. Okay, so for part B, first thing what we're going to do, exactly the same thing as our binomial one, we're going to write down H0 and H1. Well, our null hypothesis is going to be a student claimed that the mean height of adult men from region B of this country was different from the mean height from A. So our null hypothesis was they weren't different, they were actually the same, the mean heights. So we're actually going to be looking at the mean heights, which was going to be 175.4. That's going to be our null hypothesis. Well, our alternate hypothesis, this is the actual argument he's making, is that they are different. So we're going to say mu is not equal to 175.4. Okay, cool. Next, what we're going to do is just make our distribution. Let's not use x, let's use y. Normally distributed by, we're going to take the same mean that we used, 175.4. And we're also going to have our same standard deviation like they've said in the question. However, this differs because this time we've actually got a random sample size of 52. So what we need to do is actually divide this by 52.
the bigger your sample size is, the smaller your standard deviation becomes, and essentially your data becomes more accurate. Like you have more accurate data in a group of 1,000 people compared to like 10, right? And you can actually put a bar up above this. You don't have to, but normally there's like a bar to kind of, it's just a bit of notation. All right. Now in our binomial question, we had a key value, and we actually do have a key value here as well of 177.2, and we will kind of just test this. Does this, fit within the 5% significance level? So what I'm going to do is quickly draw a normal distribution curve, and we can think about this visually. So in the middle, our mean is 175.4, and the key value is saying 177.2. Well, 177.2 is not going to be on the left. It's actually going to be on the right hand side, right? And on both of your side of the normal distribution, because this is a two-tailed test, because it's a not equal to, essentially we have to kind of look at both sides of the tails and kind of see, okay, do we have this value fitting within it or not? But we need to see how much it is in terms of our probability. Now overall our significance level is 500. Now overall our significance level is 5%. So that means that these tails, these sections here, have to add up to 5%. So one of the tails must be 2.5% if we just half them, right? And we need to check, is this 177.2 outside it, or is it actually within it? That's what we're testing. Well, at the moment you can see 177.2 is on the right hand side of the equation, or the curve I should say, not the equation, the curve. So what we're going to test is essentially the probability that y bar is bigger than 177.2, and we're going to check, is it actually bigger than 2.5% or is it less than 2.5%? And let's just put that into our calculator. So into our calculator with this data, we're going to have bigger than 177.2, really big number. We've already got that as our upper. Our standard deviation, you have to be careful here. I would probably put this in brackets. So we have 6.8 actually. Yeah, so I'll do square root of 6.8 squared divided by 52. So that's your whole variance, and you're going to square root it for your standard deviation. And then in your mu, well, your mu is 175.4, which we've already got. Okay, and click equals. Well, this gives me 0.02814. So that means that this whole probability here is going to equal to 2.8%. Well, you can see that's bigger than 2.5%. If it's bigger than 2.5%, it's not in our significance level. Okay. Therefore, we cannot reject H0. We cannot, or you can say accept H1. Accept H0. Okay. We have insufficient evidence to support its claim. I don't know who the guy is. What's his name? Just the claim. So the claim of the student, the insufficient evidence to support that the mean heights vary between country A and country B. I'll just put A and B. Okay, and that's it. For part C, it's actually very simple. It says find the probability for the test in part B. Oh, sorry, find the p-value for the test. Now, most of the times it is, from the calculator itself, but because it's a two-tailed test, what we actually have to do is just times it by 2. So the value you get from the calculator, which is 0.02814, we just have to multiply this by 2. And that's going to be probably like 0.056. 0.02814 times by 2, 0.05628. Okay, and that will be your final probability, or your final p-value for this test, because it's a two-tailed test. Question 5. Tissam is playing a game. She uses a ball, a cup, and a spinner. And we've got a random variable distribution here, where x represents a number the spinner lands on, and we've been given the table. A, B, C, D are probabilities, and I'm just going to write this down. sometimes it's good to, have it in front of you. A plus B plus C plus D equals to 1. I know it's obvious, but I think it's just good to have it down. The spinner is spun to obtain a value of x. Cool. And then she stands x centimeters away from the cup and then tries to throw the ball into the cup. Cool. And the event S represents the fact that she actually does throw the ball into the cup. Given that she stands away some distance from the cup, when she scores, so S, our probability is going to be K over X. Okay. We'll use that in a second. And this part here, the probability of S and one of these, okay, should be the same whatever value of X is obtained from the spinner. So I'm going to call this lambda. Essentially, this is a constant. So no matter what distance we have, it's just a constant that remains the same throughout every single throw. And let's start with this for this first section. So what I'm going to do, because this part A, it says show that C is equal to 8 over 5B. I'm actually going to be focusing on these two bits. We probably don't need A and D, so I'm probably going to be focusing on this. I'm going to take a screenshot of this table, and then let's bring this down. Where is it? Let's bring this down here. And let's also bring these notes down as well, just so I don't have to scroll back up over and over again. Okay. Cool. So let's start with 50. It says that probability that S, given that X is equal to 50, is equal to K over 50, because that's the value of X. Now let's actually work out what this is. What is this given as in terms of another formula? Well, there is a formula given to you in your formula book, but I recommend that you go ahead and learn this. Probability that A given B is the same thing as probability of A and B over the probability of B. Therefore, if we kind of use the same formula for this, we actually end up with the following. The probability of S and X equals 50 all over probability that X equals 50. And that equals to K over 50. Cool. Well, at the beginning, we know that this part here is always a constant. It should be the same whatever value of X is obtained from a spinner. So it's a constant. I'm just going to call it lambda. So on the numerator, we have lambda. On the denominator, we have probability of X equals 50. Well, that's given as B. And this equals to K over 50. I'm going to do the same for 80 centimeters here. I'm going to make the next formula really quickly. So that's going to be probability of S is given that X is equal to 80, is going to be K over 80. And then I'm just going to substitute that into the formula. S and X equals 80 over the probability of X equals 80 is equal to K over 80. We know that this numerator is a constant. No matter what value of X, it's still going to remain the same. So this is actually the same thing as lambda over, but what's the probability of X equals 80 in our table? Is C. So we have lambda over C is equal to K over 80. Alright, now we kind of have some sort of simultaneous equations that we can potentially work with. We've got lambda over B is equal to K over 50, and lambda over C is equal to K over 80. I'm going to get rid of the K's. We need to get rid of the K's and the lambdas somehow. So what I'm going to do is rearrange both of these for K's. So I end up with lambda, or even 50 lambda over B is equal to K. So I have just times by 50 on both sides. Similarly here, 80 lambda over C is equal to K. And I'm going to equate these both together. So I end up with 50 lambda over B is equal to 80 lambda over C. And you can see we have lambdas in both sides. So I'm just going to divide through by lambdas. 50 over B is equal to 80 over C. I'm also going to divide through by 10. So 5 over B is equal to 8 over C. Now the original question was asking us C equals something. So we're going to try to rearrange for C. So I'm just going to times both sides by B. So that gives me 5 is equal to 8B over C. So I can swap these two around. So that means that C is equal to 8/5 of B. And that is the same that's given to us here. Amazing. Question B, find the probability distribution of X. Well, we know that B is, C is equal to 8/5 of B. Okay, and we can probably actually do the same thing to work out A and D. Now, I'm not going to make one for A and D separately. I'm actually going to probably choose B or C and then pick this other letter here. And that way we can work out A very, very nicely in a different way. I'll show you in a second. So let's choose B and D, or let's choose B and A. You just have to choose one. I would recommend you choose one that you've already used. Okay, so you can use C as well. So I'm just going to use B and D. So I'm just going to quickly write down the formula again of this. So I can just really, really quickly substitute all of the values in without, writing this down again. So I know that it's going to be on the numerator, just like before. It doesn't matter what's on the numerator, it's always going to be a constant. So I'm actually going to really abbreviate this lambda on the numerator. On the denominator, what we have is this probability of B. So in this case, this is going to be the probability of X equals X. At the moment, we're just concerned about this part here. So that's just going to be probability of X equals 50, which is just B, is equal to K over 50. I'm going to do the same thing for the next one here, 100. So that's going to be lambda over D is equal to K over 100. Cool. Let's go ahead and rearrange this. 50 lambda is equal to, or 50 lambda over B is equal to K. 100 lambda over D is equal to K. I'm going to equate both of these equations together. 50 lambda over B is equal to 100 lambda over D. We can start to cancel out some stuff. We can cancel out lambda. We can also cancel out a 10. And I'm going to make this a D equals, so it's still in terms of B. So I end up with 5D over B is equal to 10. And that means that I can also divide through by 5. I just realized D is equal to 10 B over 5. Therefore, D is equal to 2B. Perfect. Next, we knew right at the beginning here, A plus B plus C plus D is equal to 1. Well, I know that B is just equal to B. I know that C is equal to 8/5 of B. I know that D was 2B. So I'm going to quickly do the exact same thing using A. So we have lambda over B equals K over 50. And we get lambda over A is equal to K over 20, I think it was. Yeah, 20. Okay, these are the next two equations I'm going to be doing. Exactly the same thing. 50 lambda over B is equal to K, and that equals to 20 lambda over A. Divide through by 10. And then I'm also going to make this into equal to A. So this becomes, if I quickly rearrange this, 2B over 5 is equal to A. So 2/5 B. Okay, perfect. So now I've got an expression here. 2/5 B plus 8/5 B plus 2B is equal to 1. I can combine this together in my calculator. And this makes the following. 2/5 plus 1 plus 8/5 plus 2. That gives me 5B is equal to 1. Therefore, B is a fifth. Now, obviously, we need to make a probability distribution, so we should probably work out each individual one of these. So that means if B is a fifth, and this is A, this is B, this is C, and this is D, correspondingly, well, this is going to be this one's going to be 2/5. 8/5 of B is just 8 over 25. Okay, because since you're multiplying 8 over 5 times by 1/5. This one's just going to be 1/5, and this one's going to be 2 over 25. Well, that's it. That's our probability distribution more or less done. You should probably make a table just out of good habit. Okay, 20, 50, what are the numbers? 80 and 100. And then we can just bring the probabilities down into here. And that will be our final distribution. Part C. Nav tries a large number of times to throw the ball into the cup from a distance of 100 centimeters. He successfully gets the ball in the cup 30% of the time. Giving a reason why Tissam's model of the game is not suitable to describe nav playing the game for all values of x. So you're saying that essentially, given that our distance is 100 centimeters and he gets it into the cup, our probability of that is equal to 30% of the time. Or we should say 0.3. Let's apply that onto our formula. Let's see what that happens. Let's experiment with this. So this becomes S and x equal to 100 divided by probability of x equal to 100. Well, obviously at the top we know is some sort of constant. On the denominator, it's just a probability of what this is. Well, this is going to be, in our case, 2/5, right? So we have 2/5 on the bottom, so I'm going to call this 0.4, and this is going to equal to 0.3. Lambda, that means that lambda in this case, in our calculator, I believe will give us 0.12. Oops, I just typed in 0.12. 0.4. Yeah, gives us 0.12. Okay. However, let's try this with a different value. Let's try 0.12 with maybe, I don't know, 20 centimeters. Okay, so let's check if this 0.12 is actually a valid value for a constant. So let's try probability of S given x is equal to 20 centimeters. Well, again, this is going to be a quick abbreviated way from our before, which we had lambda over blah, blah, blah. So our lambda is just going to be 0.12. Our denominator is going to be the probability of x equals 20, which is 2 over 25. What is this probability here? Well, this is going to be, let's check what 2 over 25 is. 0.08. And actually, I don't even have to work this out. This has to be bigger than 1. Can we have a probability bigger than 1? No. Probability cannot be bigger than 1. Okay, therefore your model doesn't work. Okay, try it with different values. If it works with 80, great. If it works with 50, great. Just try to, the question's asking why it's not suitable. So try to find a reason for it to not be suitable. For question 6, I kind of just separated the different parts. So we've got part A here. A medical researcher is studying the number of hours T a patient stays in hospital following a particular operation. The histogram on the page opposite summarizes the results for the random sample of 90 patients. So we've got the total amount of patients, and we're trying to estimate the probability between 10 and 30 hours. Cool. So when we're working with histograms, a good thing to think about is, well, how do you work out the area underneath the histogram, or what does it represent? Well, the area underneath represents the frequency, and how you work it out is going to be your frequency density multiplied by hours. You can kind of think of it as like width times height. How do you work out area? That kind of thing. So 10 is like here, and 30 is here, and essentially what we're working out is the area underneath this, well, between this section here. So let's think about, well, what's our increments first. That's a good place to start. So the increments on our histogram, this is 6 maybe, this is 7, 8, 9, 10. Okay, so every 2 squares represents one hour. So that means that the final bit here, this is 11, this is 12 hours. If this is 15, this is 16 hours. That's 20 hours, 25. Okay, cool. All right, so that means our length here is 2. Our length here is 2. What's our frequency density? Well, our frequency density goes, the frequency density, this is 4.1. If this is 4.5, 4.1, 4.2, 4.3, 4.4, 4.5. So our increments is in 0.1s. That means that this is going to be a 4.2. Perfect. Cool. So that means our frequency here, it's going to be 4.2 multiplied by 2, which is just going to be 8.4. Perfect. We're going to do the exact same thing for the rest. Well, this length here is 4. Our frequency density is also 4. 4 times 4 gives us 16. Let me clean that up. That looks a bit dodgy. There we go. Exactly the same thing here. Length is 4. Frequency density here is 3.5 this time. In our calculator, let me try to do that in my head. 12, 14, I think. 3.5 times by 4 is 14. Cool. And then we do the exact same thing here. Our frequency density is 1. Our length is 10, so that means our area here is 10. So our total amount of people is going to be 16 plus 14 plus 10 plus 8.4. And that gives us 48.4 people in total. Perfect. Now, it's a probability, so we're going to be dividing this by 90. And that gives us as a probability of divided by 90, 0.5378. Okay, perfect. Now, part B of the question. For these 90 patients, time spent in hospital following the operation had a mean of 14.9 hours and a standard deviation of 9.3, and is given as a normal distribution. With reference to the histogram, state giving a reason whether or not Thomas's model could be suitable. Well, first of all, normal distribution is symmetrical. Okay, so this model, this is the first thing I see, this model is not symmetrical. Okay, the second thing you talk about is potentially about, actually, I wouldn't talk about continuous data. You can have continuous data here, so I think this is probably the only thing you can talk about here. It's about the idea of symmetry. You could probably somehow talk about the curves, curvature data. I guess that could link to continuous data in a way. I think the main thing here would be talking about symmetry though. Okay, cool. Part C of this question. Zhang suggests that the frequency polygon based on this histogram could be modeled with this graph here. Okay, where x is measured in tens of hours and k is a constant, and use algebraic integration to show that. Okay, well this is just pure maths here. All right, well this is going to be using your integration by parts. I'm actually going to be using the DI method really quick. So you can do this if you are running out of time. However, I would recommend that you use the integration by parts as much as you can. So the DI method essentially means you pick a variable where one of the variables is going to differentiate to 0 at some point. So for example, x in this case, x differentiates to 1 and the 1 differentiates to 0. And then e to the minus x just continues to integrate to infinity. So d just means differentiate. So I'm going to put down x here. X differentiates to 1, 1 differentiates to 0. E to the minus x we're going to integrate. E to the minus x integrates to minus e to the minus x. And then this again just flips. And then on the side here, plus, minus, plus. I'm going to draw angled arrows like so. And essentially this is my integration solved. Between my limits of 0 to n, this is going to be minus x e to the minus x minus e to the minus x. Perfect. Now what we're going to do is substitute the limits in. So when we have n, this is going to be minus n e to the minus n minus e to the minus n minus 0 minus 1. So this becomes minus e to the minus n minus e to the minus n plus 1. I'm going to factorize out an e to the minus n from here, so we just end up with this form. So this becomes minus... in fact, let's not do the minus first for now. Do e to the minus n minus 1 plus 1. We can factorize our minus 1 out, so this becomes positive. So that becomes minus e to the minus n times by n plus 1, which is the same thing as this. Part D. Show that for Zhang's model, k is equal to 99 to the nearest integer. Okay, so Zhang has said that this is the model, and to be fair, we've even got a range with this, which is really good. And So he's saying that the maximum value of his model is 4, and this kind of reflects well because it said that x is measured in tens of hours, and in a histogram you can see 40 hours. That's going to be 4 as your n or x value. So what we're going to do essentially is we're going to be doing our integration on this and substituting our values in. So we're doing the integration of kx e to the minus x between 0 to 4, and we can actually move this k out, and you can see we did this in part C, right? We already made an equation for this in part C, and this equation is this here. So this is essentially, this is essentially k multiplied by all of this is equal to 90. And I'm actually going to clean this up because I don't like the way it's looking. N plus 1 e to the minus n. Okay, and this is between 0 and n already. So we know that our upper limit is 4. And that's kind of what we solve for, because 0 and n, it doesn't matter what n is. We know our upper limit is 4. So essentially, I'm going to sub in the value of 4 here, like so. So this becomes k times by 1 minus 5 e to the minus 4 is equal to 90. Now we need to go ahead and solve for this, and we can actually just go ahead and divide by this because this is a constant. This number here inside the brackets, this is a number. We have no kind of like unknown numbers. So we can just do k is equal to 90 divided by 1 minus 5e to the minus 4. And in our calculator, if we type in 90 over 1 minus 5e to the minus 4, we get 99, which is great. And I think that's the question, what the question was asking for. Yeah, sure, that is equal to 99. Perfect. Part E. Estimate probability that 10 is less than t less than 30 using this. This is just going to be straight into our calculator. We're going to go into our normal distribution. Normal, NCD, we're going to be doing 10, 30, and then just subbing in the numbers. Our standard deviation is 9.3, our mean is 14.9, and the answer we get is 0.6486. 0.6486. Young's curve with equation 99x. Estimate 10 to 10 is less than t using this curve. Okay, so our lower time here is going to be 1. Our upper time here is going to be 30. So essentially, for part 2 here, we're going to be using the equation up here that we just worked out. Because this is 2 marker, we should probably try to use the limits that we've kind of worked out here. So essentially, it's between 0 and n, we have to think about how the integral kind of subtraction works. If we want to work out between, this is going to be x equals 1 and x equals 3, right? Because it's in tens of hours. If we want to work out any sort of integral between that, essentially, if I just draw a random curve, nothing related, this is between 0 and 3. And 0 and 1 is like here, right? Well, to work out this middle section, what we have to do is work out 0 to 3 minus 0 to 1. And that will help us work out this middle section. And that's how we can use this limit here. And essentially what we have is this limit multiplied by 99 because we have a constant behind here of 99. Okay, so using this limit, and let me take a screenshot of this limit here. This limit equation. Using this, essentially what we have is the following: 99 times by x equals 3 and x equals 1. That's our limits. 1 minus that's going to be 4e to the minus 4. 4e to the minus 3 even, minus 1 minus 2e to the minus 1. What does that give you as a number? No idea. And let's just put that into the calculator. 99 brackets. Let's actually not even do brackets yet. Let's do 1 minus e to the 4e to the minus 3. And then minus 1, make sure you have brackets, 1 minus 2e to the minus 1 times this whole expression by 99. Calculator disappeared again. There we go. And that equals to 53.12. But back in the question, it said a probability. Can we have a probability bigger than 1? No. Okay, and we do know that the whole amount of people add up to 90, so I'm just going to divide this answer by 90. And what that gives me is 0.590. Or was it 591? 590. Cool. Part F, and this is the last part of the paper. The researcher decides to use Young's curve to model A is less than T less than B. State one limitation of the model. Well, Young's model, we know that the maximum is up to 4. Chances are patients can stay longer for 40 hours. Okay, and that's the limitation of his model. Alright, that is the stats paper done.